Picture this. Right now, as you watch this video, our planet is hurtling through space at 107,000 kilometers per hour, orbiting the sun as it hurtles through the galaxy. And in this endless ocean of space, there are objects so powerful, so destructive, that they can wipe out our civilization in the blink of an eye. Not in millions of years. Not tomorrow. Right now. Let's start with what seems to be the most obvious: asteroids. But forget everything you've seen in Hollywood movies. The reality is much scarier and at the same time, much more interesting. The asteroid that killed the dinosaurs 66 million years ago was only about 10 to 15 kilometers in diameter. Only. This is the size of a small city. But the energy released by its collision with Earth was equivalent to the explosion of 10 billion atomic bombs dropped on Hiroshima. Imagine this number, 10 billion. When this asteroid crashed into the Yucatan Peninsula, it broke through the Earth's crust to a depth of several kilometers in a matter of seconds. The temperature at the point of impact reached tens of thousands of degrees. The rocks evaporated instantly. The shock waves spread throughout the planet. A kilometer-high tsunami washed away everything in its path. But the worst thing began later. Trillions of tons of dust, ash, and soot rose into the atmosphere. The sun disappeared for months, perhaps years. The temperature on the planet has fallen by tens of degrees. Photosynthesis stopped. Food chains collapsed. 75% of all species on Earth are extinct. And now for the frightening part. These asteroids are still out there in space, and they're flying right now. NASA tracks about 2,000 potentially hazardous asteroids, but these are only the ones we have been able to detect. Their orbits cross the Earth's orbit. Each of them is capable of causing a global catastrophe. And here's what really keeps astronomers on their toes at night. We only see asteroids that reflect enough sunlight. Dark asteroids, those made of carbonaceous materials, are virtually invisible against the background of space. They may be approaching, and we won't even know it until it's too late. There's an asteroid called Bennu, a space rock about the size of the Empire State Building. NASA is so concerned about its orbit that it has sent an entire mission there, taken soil samples, and is studying it like a doctor studies a dangerous tumor. Why? Because there's a tiny but real chance that Bennu could collide with Earth in the late 22nd century. One chance in 2700. Sounds unlikely? It's possible. But it's like getting on a plane knowing that 1 in 2,700 flights will crash. Would you fly? But Bennu is just a kid compared to the real monsters out there in the asteroid belt between Mars and Jupiter. There is Ceres, a dwarf planet with a diameter of almost 1,000 kilometers. There is Vesta, Pallas, Hygeia, huge stone worlds. If some incredible gravitational cataclysm were to hurl even one of them towards Earth, it wouldn't be the end of civilization. That would be the end of the entire biosphere. The oceans would boil away. The atmosphere would have broken down. The Earth would turn into a red-hot, lifeless ball of molten rock. And you know what's the most terrifying thing about asteroids? We may not see the threat approaching at all. In 2013, a meteorite with a diameter of only 17 to 20 meters exploded over the Russian city of Chelyabinsk. Only 17 meters, the size of a small house. But the blast wave shattered windows in thousands of buildings, injuring more than 1,500 people. The energy of the explosion was equivalent to 30 atomic bombs. And we did not know that he was flying towards us. No one, not a single observatory in the world. It came from the direction of the sun, where our telescopes are blind to the bright light. We saw it only when it was already burning in the atmosphere. Now scale it. Imagine an object not 17 meters, but 100 meters, or 500, or a kilometer, approaching from the direction of the sun. Invisible, silent, unstoppable. The first thing we will know about it will be a bright flash in the sky, and then nothing, because there will be no later. But asteroids are only one kind of threat. Let's talk about comets. Oh, comets are a whole other level of danger. Asteroids mostly stay in the plane of the solar system. Their orbits are relatively predictable. Comets are cosmic madmen. They come from the Oort cloud, a giant spherical cloud of icy bodies that surrounds the solar system at a distance of almost a light year. Yes, light years. This means that light, the fastest thing in the universe, travels from the sun to the edge of the Oort cloud for an entire year. There are trillions of comets in this cloud, trillions of ice bombs just drifting out there in the cold and darkness. And from time to time, something bothers them. A passing star, a gravitational perturbation, a collision between comets. And one of them begins to fall toward the inner part of the solar system. To us, comets move incredibly fast, up to 70 kilometers per second. That's twice as fast as most asteroids. This means much more kinetic energy in a collision. The energy of the impact is proportional to the square of the speed. Remember? Double the speed, quadruple the destructive power. A comet the size of a Chelyabinsk meteorite would produce an explosion 4 times more powerful. A comet the size of a dinosaur killer asteroid, it's scary to even think. But there's more. We may not see a comet approaching until the very last moment. Do you remember Halley's Comet? Its orbital period is 75 to 76 years. We know when it will return. But long-period comets? The ones that come from the Oort cloud? Their orbital period could be millions of years. Or they may never return at all, flying through the solar system once and leaving forever. We can detect such a comet just a few months before a potential collision. A few months to understand that our civilization is coming to an end. In 1994, something happened that made all the astronomers in the world gasp at the same time. Comet Shoemaker-Levy 9 collided with Jupiter. But it wasn't just any comet. It broke up into 21 fragments before impact. And within a week, these fragments bombarded Jupiter one after another. Some of the explosions were so huge that they left dark scars the size of Earth. From Earth, on Jupiter, a planet that is 1,300 times larger than ours in volume. The energy of just one of these impacts was equivalent to 6 million megatons of TNT. This is 300 million Hiroshima. If even one of these fragments had made it to Earth, we wouldn't even have memories. And Jupiter, by the way, is our protector. Its gravity is constantly intercepting comets and asteroids that could fly towards the inner planets. Jupiter is a cosmic vacuum cleaner, a cosmic guardian who takes the blows for us. But even he can't catch everything. Something slips through. Something always slips through. Now let's talk about something truly terrifying. Gamma ray bursts. If asteroids are bullets and comets are cannonballs, then gamma ray bursts are science fiction death rays that have become a reality. These are the brightest events in the universe. When a gamma ray burst occurs, it shines for a few seconds or minutes brighter than all the stars in its galaxy combined. All hundreds of billions of stars. And all this energy is focused into 2 narrow beams, like a giant cosmic beacon of death. What causes gamma ray bursts? Usually these are the death of massive stars, hypernovae. When a star 20, 30, 40 times more massive than the sun runs out of fuel, its core collapses into a black hole or neutron star in a fraction of a second. The outer layers of the star collapse inward, then bounce outward in a cataclysmic explosion. And at this moment, two beams of pure gamma radiation shoot out at the poles of the dying star. Gamma rays are the most energetic form of electromagnetic radiation. They are so energetic that they can tear apart atoms, split DNA molecules, and destroy all living things. If a gamma ray burst occurs in our galaxy, and one of its rays is directed at Earth, we may not even have time to understand what happened. Gamma rays travel at the speed of light. We will see a flash and at the same time receive a lethal dose of radiation. Not first we will see, and then we will receive. Simultaneously, because there is nothing faster than light. There will be no warning. What will happen to the Earth? Imagine that half of the ozone layer disappears within a few seconds. Ozone, which protects us from solar ultraviolet radiation. Suddenly, the sun, our source of life, becomes the source of death. Ultraviolet light falls on the surface of the planet without any obstacles. Phytoplankton in the oceans, the backbone of the entire marine food chain, are starting to die. Plants on land receive lethal doses of radiation. Animals going out into the sunlight get skin burns and eye damage. But this is just the beginning. Gamma radiation interacts with the atmosphere, creating huge amounts of nitrogen oxides. These chemical compounds destroy what's left of the ozone layer and cause acid rain all over the planet. Acid rain that destroys crops, poisons water bodies, and kills forests. And then, nuclear winter. The same nitrogen oxides form a brown haze in the upper atmosphere, blocking sunlight. The temperature drops. Photosynthesis slows down to a complete stop. The global food chain is collapsing. Sounds like the end of the world? This can happen at any time. Astronomers have calculated that in the Milky Way, a gamma ray burst occurs about once every few million years. And if it occurs within a radius of about 6,000 light years from us, and its beam is pointed in our direction, it could mean a mass extinction. 6,000 light years sounds like a huge distance, doesn't it? But in our galaxy with a diameter of 100,000 light years, this is practically next door. It's like living in a big city and saying, oh, the explosion happened just a few kilometers away. Technically far away, but actually dangerously close. And there are real candidates. Eta Carinae is one of the most massive and unstable stars known to us. It is 100 to 150 times more massive than the Sun and 5 million times brighter. It is so unstable that it has already exploded several times, but each time it somehow survived. But this cannot last long. Sooner or later, Eta Carinae will explode for real. And when it does, it will be one of the brightest gamma ray bursts in the history of the galaxy. It is 7,500 light years distant. This is a little further than the danger zone, but not much. And we do not know exactly where its poles are directed. They can be directed at us, or not. We just don't know. The good news? This Carina could explode tomorrow, or in a million years. Stars don't have a schedule. The bad news? If it exploded 7,500 years ago, light and gamma rays are still flying towards us through space. Right now, could be, and we will know about it only when they reach us. But let me tell you about an even more terrifying possibility. Short gamma ray bursts. While long gamma ray bursts occur when massive stars die and last seconds or minutes, short gamma ray bursts last less than 2 seconds. 2 seconds of absolute hell compressed to an instant. What causes them? Merger of neutron stars or neutron star with a black hole. Neutron stars are the remnants of massive stars that have collapsed under their own gravity. They are so dense that a teaspoon of neutron star matter weighs 1 billion tons. 1 billion tons in a teaspoon. Gravity on the surface of a neutron star is 200 billion times stronger than Earth's. If you got there, you wouldn't just be crushed. You would be crushed to the atomic level, reduced to a layer 1 atom thick on the surface of a star. When two such stars collide, and they collide when their orbits gradually degrade due to the radiation of gravitational waves, more energy is released per second than the sun will release in its entire 10 billion year lifetime. And most of this energy is released in the form of gamma radiation. It's a bright, dazzling, killer burst of light and radiation that can sterilize entire regions of the galaxy. There is a theory that one of the mass extinctions in Earth's history, the Ordovician-Silurian extinction event about 450 million years ago, when approximately 85% of all marine species died out, was caused by a gamma-ray burst. Of course, dinosaurs did not exist then. There were almost no fish. But life in the oceans flourished: trilobites, brachiopods, graptolites, and all of a sudden, most of them were gone. Fossils show signs of mass extinction, but there is no sign of volcanic activity or asteroid impact. Just sudden death. Some scientists think it could have been a gamma-ray burst that struck Earth, destroyed the ozone layer, and doomed marine life to extinction from ultraviolet light and starvation. And the worst thing? We will never know in advance. A gamma-ray burst travels at the speed of light. No warning. There is no way to prepare. No way to defend yourself. We'll just one day see an extraordinarily bright star in the sky. So bright that it can be seen during the day. And at that moment, our atmosphere will begin to collapse. Now let's turn our attention to our home star, the Sun, a huge fusion reactor in the sky that gives us life. Without it, we would be a frozen, lifeless rock drifting in the dark. But the Sun is not just a stable light bulb in the sky. It's a bubbling inferno of plasma, with temperatures of 15 million degrees in the core and magnetic fields so powerful that they can tear apart atoms. Every 11 years, the Sun goes through a cycle of activity. Magnetic fields are rearranged. Sunspots appear and disappear. Coronal mass ejections hurl billions of tons of plasma into space. It is okay. This is natural. This has been happening for billions of years. But sometimes, very rarely, the Sun does something truly extraordinary. Something terrifying. A superflare. In 1859, what is now called the Carrington event took place. British astronomer Richard Carrington was observing the Sun, thankfully through the appropriate filters, when he saw a bright flare on the surface. For the next 17 hours, a cloud of magnetized plasma raced toward Earth. When it reached our planet, the light show began. The northern lights were visible all the way to the Caribbean islands and Hawaii. People in the Rocky Mountains would wake up at night thinking it was morning and start making breakfast until they realized it was just a glow in the sky. Telegraph systems around the world were going crazy. Operators received electric shocks. Telegraph paper lit up right in the machines. Some telegraph lines continued to operate even after they were disconnected from power sources. The induced magnetic currents were so strong. Sounds beautiful, doesn't it? But let's fast forward to 2025. Imagine that such a superflare is happening now. We live in a world completely dependent on electricity and electronics. When a geomagnetic storm reaches the Earth, It induces electric currents in any long conductors, power lines, pipelines, railway tracks. These currents overload transformers, causing them to explode or melt. And the worst thing is that high-voltage transformers, the basis of our power grid infrastructure, are not mass-produced. They are custom-made. Each costs millions of dollars and takes months to make. What will happen? Power grids will collapse around the world at the same time. If they do not turn off carefully, they will explode. Hospitals will lose power. The cooling systems of nuclear reactors will fail. Water pumping stations will stop. Telecommunications will disappear. The internet will cease to exist, not temporarily, but for months or years until new transformers are manufactured and installed. Every satellite in orbit will be damaged by radiation. GPS will stop working. Planes in the air will lose navigation. Financial systems will grind to a halt. Supply chains will collapse, and we can't just fix it quickly. Imagine, factories are needed to produce new transformers. In order for factories to work, electricity is needed. To have electricity, you need transformers. It's a vicious circle. Civilization will fall into a trap from which it will be incredibly difficult to get out. The National Academy of Sciences has estimated that a superflare on the scale of the Carrington event today would cause $2 trillion in damage in the first year alone, and recovery would take 4 to 10 years. 10 years without electricity. Imagine this. Modern society simply cannot function. People will start dying within weeks. Not from the outbreak itself, from the consequences, from the lack of water, because the pumps do not work, from the lack of food, because supply chains are destroyed and refrigerators do not work, from the lack of medical care, from a cold in winter and the heat in summer, from diseases because the sewerage systems failed. Cities will turn into death traps. Millions, perhaps billions of people will die not from cosmic radiation, but from the collapse of infrastructure. And here's what really worries scientists. Carrington's event was powerful, but not the most powerful possible. In 2012, on July 23rd, the sun ejected a superflare about twice as powerful as the Carrington event. It swept exactly through the part of the Earth's orbit where our planet was a week earlier. We missed the apocalypse for 7 days. 7 days. If the Earth had been a week ahead in its orbit, or if the sun had ejected this flare a week later, right now we might still be recovering from the biggest catastrophe in modern history. Physicist Daniel Baker of the University of Colorado said of the event, "If this flash hit us, we would still be sorting through the wreckage." It was in 2012, more than 10 years ago, and we would still be sorting out the wreckage. How likely is this? Scientists have calculated that the probability of a Carrington-scale superflare in any given 10-year period is about 12%. In the next 10 years, there is a 1 in 8 chance that this will happen. 1 of the 8. This is not some distant theoretical possibility. This is a real, measurable threat, and we do practically nothing to prepare for it. But even superflares pale in comparison to what I want to talk about now. Wandering black holes. Let's settle for a second. Wandering. Black. Holes. Objects are so dense that their gravity curves space-time itself, creating a region from which not even light can escape. And they travel around the galaxy. Right now, invisible, silent, deadly. How does a black hole become wandering? Normally, black holes form when massive stars collapse. Most of them stay where they were born, slowly traveling through the galaxy with the stars around them. But sometimes a black hole gets a gravitational nudge, maybe from a close passage of another massive star, maybe from an interaction in a dense star cluster, maybe from an asymmetric supernova explosion that ejects it like a bullet from a gun. And this black hole begins to rush through the galaxy at a speed of hundreds of kilometers per second. How many of them are there? Scientists estimate that there may be between 100 million and a billion wandering stellar mass black holes in the Milky Way alone, from 100 million to a billion. And we know almost nothing about where they are because black holes are invisible by definition. We can only detect them indirectly by the way they bend the light from the background stars or by the way they absorb the matter that glows as it falls into them. But a single black hole hurtling through interstellar space, it is almost impossible to see it until it is dangerously close. What happens if a rogue black hole passes through the solar system? It depends on how close. If it passes somewhere beyond the orbit of Neptune, we may not even notice anything unusual. Maybe small perturbations in the orbits of the outer planets that astronomers will discover years later. But if it gets closer through the Kuiper belt or the Oort cloud, things get a lot more interesting and a lot scarier. The Oort cloud, remember? Trillions of comets drifting at the edge of the solar system. A black hole passing through the Oort cloud would shake it with its gravity, like a spoon in a cup of sugar. Thousands, maybe millions of comets would have received enough gravitational nudge to start falling toward the inner solar system. To us, imagine not one comet, not 10, but a whole swarm, a rain of comets bombarding the inner planets for centuries. The Earth would turn into a space shooting gallery, but it's still a relatively distant playthrough. What if the black hole came closer? Through the asteroid belt between Mars and Jupiter? Or, inconceivably worse, through the inner solar system where we are? If a stellar mass black hole, say 10 times more massive than the Sun, passes close to Earth, its gravity will begin to tear our planet apart before we actually get close to it. This is called tidal forces, the same force that causes the oceans to rise and fall in response to the moon's gravity, but multiplied by millions. The side of the Earth facing the black hole will be attracted more strongly than the opposite side. The planet will begin to stretch, deform, and tear apart. First, the oceans will slosh out of their basins. Tsunamis kilometers high will hit the continents. Then the Earth's crust will begin to crack. Earthquakes of magnitude that we cannot even measure on our scales will tear apart the continents. Volcanoes around the world will explode at the same time. The atmosphere will begin to escape into space, sucked in by the gravity of the black hole. And all of this will happen over the course of hours, maybe days, as the black hole approaches, passes by, and moves away. If the Earth passed close enough to the black hole's event horizon, the irreversible point beyond which nothing can escape, the planet would be torn apart into atoms by a process astrophysicists poetically call spaghettification. The gravitational forces would differ so much between one end of the object and the other that everything would stretch into long, thin strands like spaghetti. That would be, quickly at least, an unpleasant consolation. But here's the question that should keep you up at night. Could a rogue black hole be heading toward us right now? The answer is, we don't know. We can't know. An Earth-sized black hole would be invisible against the background of space. We could only detect it by gravitational microlensing. As it passes between us and a distant star, its gravity bends and amplifies that star's light. But this requires the black hole, the Earth, and the background star to line up almost perfectly. And even then, we would only see a brief flash of the star's brightness, lasting hours or days. By the time we realized that this was a black hole and not just an anomaly, it could be very close. In 2011, astronomers discovered what may have been a rogue black hole in the constellation Sagittarius, about 20,000 light years away. They only noticed it because it was just passing in front of the background star. If it hadn't aligned perfectly, we would never have known it was there. How many more are there? Invisible, unknown, traveling through the galaxy. And there's something else that is really frightening. Supermassive wandering black holes. At the center of every large galaxy is a supermassive black hole, an object with a mass millions or billions of times greater than the Sun. The Milky Way has a mass of about 4 million solar masses, Sagittarius A-. Normally, these monsters stay at the centers of their galaxies, but when two galaxies collide, it's common in space. Their central black holes eventually merge. Sometimes, during a merger, gravitational waves emitted asymmetrically give the combined black hole such a powerful push that is ejected from the galaxy entirely. At a speed of thousands of kilometers per second, such a supermassive wandering black hole passing through the Milky Way would be. Catastrophic is hardly an adequate word. Its gravity would perturb the orbits of stars light years away. Entire star systems would be ejected from the galaxy or sent into chaotic new orbits. If such an object were to pass somewhere within a few hundred light years of the solar system, gravitational perturbations could alter the Sun's orbit around the center of the galaxy, sending us into regions with a higher density of stars, more supernovae, and more radiation. Or they could send us to the edge of the galaxy, into a cold, dark void where new stars almost never form. Scientists have calculated that there may be billions of such expelled supermassive black holes hurtling through intergalactic space in the observable universe. Most of them are far, too far away to ever pose a threat. But majority does not mean all. And the universe is 13.8 billion years old. There is plenty of time for strange, unlikely events. Let me tell you about one of the most disturbing discoveries of recent years. In 2017, astronomers discovered a star hurtling out of our galaxy at a speed of 1,700 kilometers per second, fast enough to break free from the gravitational pull of the Milky Way and escape into intergalactic space forever. What could accelerate a star to such an incredible speed? The most likely explanation is that it was part of a binary system that got too close to the supermassive black hole at the center of the galaxy. One star was captured by a black hole, the other was ejected like a stone from a sling. If black holes can do this to stars, objects hundreds of thousands of times more massive than Earth, imagine what they could do to us. But wait, it's getting even scarier. Primordial black holes. These are theoretical black holes that could have formed in the first moments after the Big Bang, from density fluctuations in the early universe. They didn't require a star to collapse, so they could be any size, from subatomic to star mass or larger. And if they exist, there could be many of them. Lots of. Some scientists have suggested that much of the dark matter, the mysterious substance that makes up most of the mass of the universe, but that we can't see or directly detect, may actually be primordial black holes. If this is true, then there are not hundreds of millions of black holes in our galaxy. There are trillions of them, everywhere, drifting through the dark matter halo surrounding the Milky Way. And from time to time, one of them can pass through the solar system. A small primordial black hole, say the mass of an asteroid but smaller than an atom, would not destroy the Earth instantly. But if it were to pass through our planet, it could get stuck inside, held in place by Earth's gravity, and it would begin to slowly absorb matter from within. Atom by atom, Molecule by molecule, this tiny black hole would grow. The process would take millions or billions of years, but it would eventually swallow the entire planet from the inside out, leaving only a black hole drifting back to where Earth once was. Sounds like science fiction? Could be, but physics allows it. Primordial black holes remain theoretical, but they do not violate any laws of nature. They can exist, and if they do, we have absolutely no way to detect a small one unless it goes right through the detector or causes a noticeable gravitational effect. They would be perfect hidden killers, permeating the cosmos, invisible, undetectable, unstoppable. Now let's talk about something that keeps astrobiologists anxious: sterilization events. These hypothetical cosmic phenomena are so powerful, so pervasive, that they could sterilize not just one planet, but entire regions of the galaxy at once. We've already talked about gamma-ray bursts, but there's more. Supernova explosions. When a massive star explodes, it briefly shines as brightly as an entire galaxy. But light is the least of the problems. A supernova ejects a huge amount of cosmic rays, high-energy particles moving at almost the speed of light. These particles can damage DNA, cause cancer, sterilize the surfaces of planets. And they continue to come for years, decades, centuries after the explosion, as the shock wave expands through space. If a supernova occurs within about 50 light years of Earth, it could spell a catastrophe for life on the surface. The ozone layer will be damaged. The levels of cosmic rays on the surface will increase hundreds of times. Mutations will increase. Cancer will become an epidemic. But perhaps civilization will survive. We will be able to take shelter, wait out the storms, recover. It's possible, but there is an even more ominous possibility. Kilinovae are explosions during the merger of neutron stars, which we discussed earlier in the context of gamma-ray bursts. These events don't just produce gamma rays. They also produce huge amounts of heavy radioactive elements. When two neutron stars merge, they eject matter enriched in elements heavier than iron, gold, platinum, uranium. A lot of uranium. And these radioactive elements spread through space along with the rest of the emissions. If a kilonova occurs close enough, the Earth could pass through a cloud of these radioactive particles. They will fall into the atmosphere, settle on the surface, and get into food chains. Radioactivity on Earth will increase dramatically. Not as drastically as a nuclear war. It would be spread across the planet and stretched out in time, but enough to significantly increase background radiation by millions of years. Cancer, genetic damage, reduced life expectancy, slow poisoning of the entire biosphere. There is evidence in the geological records of the Earth that something similar happened about 2 to 3 million years ago. Researchers have found isotopes of iron, 60 in deep-sea sediments from that period. Iron, 60, is not produced naturally on Earth. It only forms in supernovae and neutron stars. Its presence on Earth means that a massive explosion has occurred somewhere nearby on a cosmic scale, and its emissions have reached us. Some scientists attribute this to the climatic changes of that period and possibly to the extinction of some species of marine organisms. We survived it, but it was close, and everything becomes even more interesting. In recent years, astronomers have begun to realize that our position in the galaxy is not accidental. The solar system is located in what is called the galactic habitable zone, a region not too close to the center of the galaxy, where supernovae and other catastrophes are too frequent and not too far away at the edge, where the heavy elements necessary for life are too scarce. We're in the Goldilocks area, just right. But even in the galactic habitable zone, we are not safe. The Sun orbits the center of the Milky Way, completing a complete rotation in about 225 to 250 million years. This is called a galactic year. And as this rotation progresses, we pass through different regions of the galaxy. Sometimes we pass through the spiral arm, a region with a lot of young, hot, massive stars that live fast and die young in supernova explosions. During these periods, the frequency of nearby supernovae increases. The frequency of gamma ray bursts increases. Cosmic rays are amplified. Life on Earth is subjected to more stress. Some scientists have suggested that mass extinctions in Earth's history correlate with our passages through the spiral arms of the galaxy. It's debatable, and the correlation isn't perfect, but the idea is intriguing. Perhaps our biological history has been shaped in part by our space travel, our rotation around the galaxy, our encounters with various cosmic threats. Right now, we are in a relatively safe region, the Orion arm, which is not actually a true spiral arm, but a small branch between the two main arms. We are in a space suburb, relatively calm, relatively safe. But this is temporary. In our movement around the galaxy, we will eventually enter more dangerous regions again. This is inevitable. The only question is when and what will happen then. Now let me tell you about something really mind-blowing. False vacuum. It's one of the scariest ideas in all of physics, in part because if it happens, there will be absolutely no warning and no way to escape. None at all. Here's the idea. Quantum field theory suggests that a vacuum, empty space, actually has energy. It's not just nothing. This is the quantum field in its lowest energy state. But what if our lower energy state is not actually the lowest? What if there's an even lower energy state and our vacuum is actually metastable, stable for now, but not truly stable? This would be what physicists call a false vacuum. If this were true, then quantum fluctuations or a high-energy event could create a tiny bubble of true vacuum somewhere in the universe. A vacuum in its truly lowest energy state. And this bubble would begin to expand at the speed of light. As it expands, it would turn a false vacuum into a true vacuum. And here's the horror. In a true vacuum, the laws of physics can be different. Atoms can be unstable. Chemistry may not work. Stars could not exist. Life would be impossible. This bubble of true vacuum would expand in all directions at the speed of light, destroying everything in its path. And remember, nothing moves faster than light. This means that there can be no warning. Generally, the light from the approaching wall of destruction will reach you at the same moment as the wall itself. You won't see her coming. For an instant, the universe exists. The next moment, she's gone. No pain, no awareness, just an instantaneous cessation of the existence of everything, matter, energy, space, time itself. And the most frightening thing in all this? Such a bubble could have begun to expand somewhere far away in the universe billions of years ago. Right now, it could be hurtling toward us through space, erasing galaxies, destroying civilizations, overriding the laws of nature. And we'll never know it until it reaches us. Astronomers look through telescopes, physicists conduct experiments, but it is impossible to detect the approaching bubble of false vacuum. That's impossible. It travels at the speed of light, and the light from its edge reaches us at the same time as the edge itself. Is it likely? To be honest, we don't know. We are not even sure that we are in a false vacuum. Most physicists believe that we are probably in a true vacuum, a stable state that will last forever. But probably is not definitely. Experiments at the Large Hadron Collider have suggested that the Higgs boson, the particle responsible for the mass of other particles, has a mass that puts our universe in a potentially metastable region. Not definitely metastable, but on the borderline. Physicists use such cautious phrases as presumably stable and possibly metastable. It's a scientific way of saying, we really hope it's okay, but we're not really sure. Is there a bubble of vacuum decay somewhere out there, rushing towards us? It's possible. Will he destroy us tomorrow? Next year? In 1 billion years? Never? We can't know. It's the quintessential uncontrollable risk, an event we can't predict, can't prevent, and can't even detect before it's too late. All we can do is hope that the calculations are correct and that we are in a true vacuum. Hope and keep living, because what other alternative? But let's get back to the threats that we can at least observe, even if we can't control them. Stellar close approaches. Stars are not stationary. They move around the galactic center, each in its own orbit, each at its own speed. Most stars will never approach each other. The distances between stars are huge compared to their sizes. But sometimes, very rarely, two stars pass close enough for their gravity to begin to affect each other's planetary systems. The nearest star to us is Proxima Centauri, just over 4 light-years away. It seems close, and by cosmic standards it is, but gravitationally it has almost no effect on us at all. But what if the star passed not 4 light-years away, but say, half a light-year, or closer? Simulations show that a star passing within 1 light-year of the solar system could significantly perturb the Oort cloud. Hundreds or thousands of comets would receive enough gravitational push to start falling towards the inner solar system. Over the next 1,000,000 years, we would experience a significant increase in cometary bombardments. Not an immediate apocalypse, but a vastly increased risk over a vast period of time. If the star were to move even closer, within a few thousand astronomical units, it could begin to perturb the orbits of the outer planets. Neptune, Uranus, even Saturn could receive gravitational jolts that alter their orbits. And this would have a cascading effect. The orbital resonances between the planets would change. The gravitational interactions that have kept the inner solar system stable for billions of years could have been disrupted. The Earth's orbit could become more eccentric, leading to extreme climate fluctuations. Or, in a worst-case scenario, the Earth could be thrown into an orbit that brings it too close to the Sun or too far away, making life impossible. And in a truly extreme scenario, if the star were to pass just a few hundred astronomical units closer than the farthest Kuiper Belt objects, it could actually capture planets. Mars, Earth, even Venus could be ripped out of their orbits by the gravity of a passing star and swept away to become orphan planets, frozen worlds drifting through the interstellar void forever. How likely is this? Quite rarely, fortunately. Astronomers have calculated that the star passes within 1 light-year of the Sun about once every few 100,000 years. A really close approach within a few thousand astronomical units occurs perhaps once every few tens of millions of years. But rarely does not mean never. And we know about some stars that are moving in our direction. Gliese 710 is a red dwarf that is currently about 64 light-years away, but it is moving towards us. In about 1.3 million years, Gliese 710 will pass through the Oort cloud, perhaps only 10,000 to 13,000 astronomical units from the Sun. This will not affect the planets directly, but it will definitely agitate the Oort cloud. The number of comets falling into the inner solar system will increase. Humanity 1.3 million years into the future, if we still exist, will face an increased risk of cometary impact for tens or hundreds of thousands of years after the encounter. 1.3 million years sounds like a long time, doesn't it? But from a geological point of view, it's just a blink of an eye. Dinosaurs became extinct 66 million years ago. Humans have existed in one form or another for about 2 to 3 million years. Civilization has existed for only a few thousand years. Who or what will we be in 1.3 million years? Will we still be on Earth? Will we be recognizable as humanity at all? Or will this encounter with Gliese 710 be a problem for our distant descendants, so altered by evolution and technology that we wouldn't be able to recognize them? But there are also threats closer in time. Let's talk about the Earth's magnetic poles. Right now, beneath our feet, Earth's outer core, a layer of molten iron and nickel about 2,300 kilometers thick, is spinning and convecting, creating electric currents. These currents produce the Earth's magnetic field, an invisible shield that surrounds the planet and protects us from the solar wind and cosmic rays. Without this magnetic field, the Earth's atmosphere would slowly evaporate into space, as happened to Mars billions of years ago. But here's the thing, this magnetic field is not stable. It fluctuates, weakens, intensifies, and from time to time, on average every few 100,000 years, it turns completely upside down. The north magnetic pole becomes south, the south pole becomes north. This is called a geomagnetic inversion, and it is a completely normal phenomenon on geological timescales. This has happened hundreds of times in Earth's history. The last complete inversion occurred about 780,000 years ago. We are overdue in terms of the average time interval between inversions, and there are signs that the next one may be coming. The Earth's magnetic field has weakened by about 9% over the past 170 years. The magnetic North Pole is drifting faster and faster, moving more than 600 kilometers since the early 19th century, and its speed is increasing. The South Atlantic anomaly is an area over South America and the South Atlantic where the magnetic field is abnormally weak, expanding. What will happen during a geomagnetic inversion? The process is not instantaneous. It takes from several hundred to several thousand years. But during this time, the magnetic field becomes very weak and chaotic. Instead of one neat dipole, one North Pole, and one South Pole, you can have multiple poles migrating across the planet's surface. The field may weaken to 10% of its current strength or less. When this happens, the Earth's protection from cosmic radiation will be greatly reduced. Solar winds, streams of charged particles from the sun, will penetrate deeper into the atmosphere. Cosmic rays from interstellar space will reach the surface in greater numbers. Satellites will be exposed to increased radiation, shortening their lifespan. Electronic systems will become more vulnerable to solar storms. Astronauts on the International Space Station or at future lunar and Martian bases will face a significantly increased radiation risk. On the surface, the effects will be less dramatic, but still noticeable. Cosmic ray levels will increase, potentially leading to higher cancer rates. Some scientists have suggested that there may be damage to the ozone layer due to an increase in cosmic rays creating chemical reactions in the upper atmosphere. This could lead to an increase in ultraviolet radiation on the surface. But the Earth has gone through many inversions before, and life has survived. There is no evidence of mass extinctions corresponding to inversions in the geological record. The real problem for modern civilization would be technological. Our electronic infrastructure, our satellites, our GPS systems are all vulnerable to increased cosmic radiation and solar storms. During a weak, chaotic magnetic field, even a moderate solar storm could cause devastation, which would normally require a very violent storm. We could face centuries of increased technological failures, the need for additional protection for electronics, shortened lifespans of satellites, and increased risks to space travel. And here's the worrying thing. We don't know exactly when the next inversion will begin. The current weakening of the field can be the beginning of an inversion, or it could just be a fluctuation and the field will intensify again. Geological records show that there have been several false starts, times when the field began to weaken and become chaotic, but then stabilized without a complete reversal. We may be at the beginning of an inversion right now, or we could be in a false start, or the current weakening may be completely normal. We just don't know. But while we're on the subject of magnetic fields, let me tell you about something really creepy. Magnetars. It is a type of neutron star with an incredibly strong magnetic field, 1,000,000,000,000 times stronger than Earth's magnetic field. Trillion. These objects are so strange, so extreme, that they barely fit into our understanding of physics. The magnetar's magnetic field is so powerful that it warps the shape of atoms. For real. Atoms in a strong magnetic field become elongated, cigar-shaped instead of spherical. If you could somehow stand on the surface of a magnetar, which is impossible for a million reasons, but let's imagine your body wouldn't disintegrate simply from gravity. The magnetic field would literally tear apart the atoms in your body. The molecules couldn't stick together. Chemical bonds would be broken. You would cease to exist at the molecular level. But here's what's really scary about magnetars. They're unstable. Their incredibly powerful magnetic fields create tensions in the star's crust, which, remember, is made up of matter billions of times denser than normal matter. From time to time, these stresses become too great and the crust cracks. This is called starquake. And when a starquake occurs on a magnet, more energy is released in 1/10 of a second than the sun emits in 100,000 years. This energy is spilled out in the form of a giant burst of gamma and X-rays. If such a flare were to hit Earth at close range, say within a few tens of light years, the results would be catastrophic. The ozone layer could be destroyed in seconds. Satellites would burn up from radiation. Anyone looking at the sky in the wrong direction could be blinded. And then there would be long-term effects, increased ultraviolet radiation, ecosystem collapse, mass extinction. In December 2004, the magnetar SGR 1806-20 produced the most powerful flare ever observed from any object outside the solar system. This star is located about 50,000 light years away on the other side of the galaxy. And yet, when its radiation reached Earth, it disrupted the satellites, affected the Earth's atmosphere, and temporarily blinded some astronomical instruments. From a distance of 50,000 light years, if this magnetar were within 10 light years, the same flare could have triggered a mass extinction event on Earth. Fortunately, there are not many known magnetars, and none of them are very close to us. The nearest confirmed magnetar is about 13,000 light years away. But there's a problem. We're not sure how many magnetars there are. They emit radiation only when they are active, when starquakes occur. A sleeping magnetar would be almost invisible. It could have been much closer, and we wouldn't have known it until it suddenly woke up and spewed a burst of radiation in our direction. Now let me tell you about something completely different, but just as frightening. Interstellar objects. In 2017, astronomers discovered something unprecedented, an object passing through the solar system that was clearly not from our solar system. He was in a hyperbolic orbit, a trajectory that meant that he came from interstellar space and was about to return to the same place. He was named Oumuamua, a Hawaiian word meaning roughly scout. Oumuamua was weird. It was elongated, perhaps 10 times as long as it was wide. It was spinning, tumbling through space, and it accelerated as it moved away from the sun, not just from gravitational interactions, but from some small extra force that scientists are still discussing. It may have been the degassing of ice turning to steam when heated by the sun, acting like a tiny rocket engine. Perhaps it was something else. Some people, of course, assumed that it was an alien probe. Most scientists disagree. It's much more likely that it was just a strange asteroid or comet from another star system. But no matter what it was, Oumuamua showed us something important. Interstellar objects pass through our solar system, probably quite often. Since then, we have discovered at least one other interstellar object, Comet 2I/Borisov in 2019. And astronomers now estimate that interstellar objects can pass through the inner solar system several times a year. We just can't see most of them because they're dark, fast, and small. See, why does it matter? Well, most interstellar objects are harmless, just space junk passing by. But not all of them are small. In space, there are orphan planets, planets ejected from their star systems by gravitational interactions, drifting through the interstellar void, lonely and cold. Some estimates suggest that there may be more such orphan planets than there are stars in the galaxy. Billions or trillions of frozen worlds wandering in the dark. What happens if an orphan planet passes through the solar system? It depends on its size and trajectory. A small planet passing through the outer system could simply perturb the orbits of some comets and leave. But a large planet, say a super-Earth several times more massive than Earth, or an ice giant the size of Neptune, passing through the inner solar system, that would be a disaster. Its gravity would perturb the orbits of all the planets it passes through. Mars could have been ejected from the solar system entirely. The Earth could be shifted into a new orbit, perhaps more eccentric, perhaps tilted, perhaps altered enough to make the climate uninhabitable. In a worst-case scenario, the Earth could collide with a passing planet, merging in a terrifying apocalyptic collision that would melt both planets and possibly shatter them into debris, which would eventually reassemble into one large molten mass. Everything on both planets would be destroyed. How likely is this? Extremely rare. Space is vast and planets are small. Even if trillions of orphan planets are drifting through the galaxy, the chances that one of them will pass close enough to the solar system to cause harm are incredibly small. But not zero. Never zero. And this brings us to the final, most philosophical thought about all these threats. The paradox of our existence. We live on a fragile planet surrounded by space, full of objects that could destroy us at any moment. Asteroids rush in their orbits. Comets fall from the Oort cloud. Gamma ray bursts cut through the galaxy at the speed of light. The sun is bubbling and exploding. Black holes drift in the dark. Magnetars crackle and spew radiation. Interstellar objects rush past. Space itself can be metastable, ready at any moment to move into a new state that will destroy everything. And yet life goes on. We wake up in the morning, go to work, love, laugh, make plans for the future. We have created civilization, art, science, technology. We've sent probes to the edges of the solar system and beyond. We split the atom and uncovered the genetic code. We look through telescopes at galaxies billions of light years away, trying to understand our fate. The fact is that life on Earth has been around for almost 4 billion years. During this time, countless cosmic catastrophes have occurred somewhere in the universe. The stars exploded, black holes collided, gamma ray bursts have traced the cosmos. And yet the Earth survived. Life survived. We survived. There have been 5 major mass extinctions in Earth's history, events when more than half of all species went extinct. Each time, life was restored. Sometimes it took millions of years, but life found a way. After the extinction of the dinosaurs, mammals rose, diversified, and filled ecological niches. In the end, some of them became us. If the asteroid hadn't killed the dinosaurs, humans probably would never have evolved. Disaster for some species has become an opportunity for others. This does not mean that we should be complacent. We are not dinosaurs unable to change our fate. We have the technology, the intelligence, the ability to anticipate and potentially prevent some of these threats. NASA and other space agencies are actively tracking near-Earth asteroids. The DART mission in 2022 successfully changed the orbit of an asteroid by hitting it with a spacecraft, the first ever planetary defense proof of concept. We can defend ourselves against asteroids, at least in theory, if we detect them early enough. We are improving our understanding of space weather, solar flares, geomagnetic storms. We can build more resilient infrastructure, protect critical systems, and prepare for superflares. We are not helpless, but we are powerless against some threats. We can't stop a gamma ray burst. We can't deflect a wandering black hole. We cannot prevent a vacuum from decaying. All we can do is know that these dangers exist, understand the risks, and perhaps eventually develop the technology to become a multi-planetary, multi-system, even multi-galactic species. To spread humanity so widely that no catastrophe, no matter how horrific, can destroy us completely. Elon Musk talks about making life multi-planetary. It's not just about exploration or adventure. It's about survival. It is about ensuring that everything we have created, everything we are, is not destroyed in one cataclysmic event. As long as all life exists on one planet, we are all hostages to space roulette. One bad dice roll, one asteroid with our name on it, one solar superflare at the wrong time, one gamma ray burst pointed our way, and it's all over. But if we become multi-planetary, if we colonize Mars, the moon, the moons of Jupiter, if we eventually go to other stars, then the destruction of one world will not mean the end of our species. Some part of humanity will survive, preserving our culture, our history, our science, and they will continue, rebuild, reach even further into space. It's a long game. It is a game that we play not with years or decades, but with millennia and eons. On the scale of individual lives, these cosmic threats seem distant, almost unreal. The chances that a gamma ray burst will hit Earth during your lifetime are negligible. The likelihood that a rogue black hole will pass through the solar system in the coming centuries is hardly worth mentioning. You will almost certainly die from something much more mundane, illness, accident, just old age. But on the scale of species, civilization, life on Earth, these threats are real. They will happen eventually. Some of them, perhaps many of them. The question is not will it happen, but when will it happen And will we be ready? Right now, at this very moment, while you sit and watch this, the universe continues. Asteroids orbit the sun, comets drift in the Oort cloud. Somewhere in the galaxy, a massive star is nearing the end of its life. In a few centuries or millennia, preparing to explode and possibly release a gamma-ray burst. Black holes travel through interstellar space. Our sun is bubbling and boiling, its magnetic fields twisting and intertwining, preparing for the next flare. The Earth's magnetic field is slowly weakening and drifting, possibly moving towards an inversion. Somewhere, perhaps, a bubble of true vacuum is expanding through space. And life goes on. The birds are singing. Children play. Scientists are conducting research. Engineers build machines. Artists create beauty. We love, we laugh, we live. Because what else can we do? We can't stop space from being space. We cannot make the universe safe. All we can do is live our lives as fully as we can, build our civilizations as sustainably as we can, and reach for the stars as fast as we can. Because ultimately, the cosmos is not malevolent. He's not trying to kill us. He doesn't even know that we exist. It is simply a cosmos, vast and ancient, governed by the laws of physics, indifferent to life, consciousness, and meaning. Asteroids don't aim at us. Gamma-ray bursts do not haunt us. Black holes don't prey on us. They just exist, doing what space objects do, orbiting, exploding, collapsing, traveling through the abyss. We found ourselves on this little blue dot, the third planet from an unremarkable star in a quiet corner of an ordinary galaxy. And we have developed the ability to look up, to ask questions, to understand. We are aware of the threats there. We understand the risks. And yet, we choose to hope. We choose to build. We choose to continue. Because the alternative, what? Give up? Despair? We could look back at all the ways the universe could destroy us and decide that everything is meaningless. But that would be wrong. The fact that we are mortal as individuals, as species, even potentially as a civilization, does not make our lives meaningless. This makes it precious. This makes every moment important. It gives urgency to our goals, our dreams, our desire to survive and thrive. We are the universe's way of knowing itself, as Carl Sagan said. We are the atoms of the stars that have become alive, aware, able to understand the cosmos that created us. And if we were destroyed by an asteroid or a comet, a gamma-ray burst or a wandering black hole, a solar superflare or a magnetic inversion, the universe will lose something. She will lose the part of herself that could see, think, ask questions. But as long as we are here, we will continue. We will continue to look to the skies, tracking threats and looking for miracles. We will continue to build, create, explore. We will continue to love and live despite all the risks, despite all the dangers, despite the fact that space is vast and indifferent and we are so small. Because at the end of the day, that's the only thing that matters. Not how we can die, but the way we choose to live. Right now, at this moment, on this fragile planet, in this dangerous space, under these endless stars, we are alive. We are aware. We're here. And this in itself is a miracle.